Chapter 9 will be over calculations from chemical equations. A little review on molar mass and Avogadro's number. Molar mass is the unit of what we have will be grams divided by moles. And you can also calculate the molar mass of a compound from the values in the periodic table using the atomic mass of each kind of element in there, adding them up. Avogadro's number is 6.022 times 10 to the power 23, and that will be used in the calculations as well. Now we want to talk more about stoichiometry. So based on what we learned in the previous chapter, we learned to balance equations to make sure both sides have the same amount. Once we balance the equation, we have the correct coefficient in front of every compound, reactants or products, and this will be used for us to get the mole ratios between those items. The coefficients here are really important. So mole ratios, for example, here we have an equation of 2H2 plus O2 goes to 2H2O. There's a relationship between hydrogen gas and oxygen gas. In this case, it will be 2 moles of hydrogen gas will react with 1 mole of oxygen gas. So that's the relationship right here. We can write it either way, top or bottom, depending on what we need to cancel off. Okay, there is also a relationship that you can talk about between hydrogen, we related to oxygen. We can also relate hydrogen to water or oxygen to water. So hydrogen to water will be 2 moles of hydrogen needs to be used to form 2 moles of water. So in this case, 2H2 to 2H2O, you can use either one depending on what we need to cancel off. And then obviously that we have the last one, a relationship between oxygen gas and water, and you have 1 mole of oxygen to 2 moles of water, or 2 moles of water to 1 mole of oxygen. So we'll use this to convert depending on the question. So if the question says if 4 moles of oxygen are present, how many moles of H2O could be formed? So the relationship here tells us that 1 mole of oxygen can be used to form 2 moles of water. If I have 4 moles, how much water can I make? So you say, I know I start with 4 moles of oxygen, and I will use this conversion factor knowing that mole to mole ratio oxygen is 1 to 2 water. So 1 mole of oxygen to 2 moles of water. You cross off the moles of oxygen, you get your units in moles of water. In this case, it will be 8 moles of water. Here's another practice question. CO2 gas plus 4H2 gas makes CH4 gas plus 2 water. Given the following chemical equation that's balanced, write the mole ratio needed to calculate the moles of water produced from 3 moles of CO2. So if you have 3 moles of CO2 and you want to find how much mole of water you need that you can make, so what you would say, you want to take 3 moles of CO2 and you put CO2 on the beginning here, and you want to convert from CO2 to water. So the mole ratio for CO2 to water is 1 CO2 to 2 water. So 1 CO2 to 2 water, and you know that you want to cross out the CO2, so the CO2 part goes on the bottom, 2 moles of water goes on the top. So your answer will be 6 moles of water. If you want to find the moles of hydrogen gas needed to produce 3 moles of water, so then you have water and you have to relate it to hydrogen gas. So the relationship between water and hydrogen gas is 2 moles of water to 4 moles of hydrogen. And you're going to start with water, which is 3 moles of water, and you want to cancel the water, so to put the 2 moles of water on the bottom, 4 moles of hydrogen on the top, cross this off, and you get your answer as 6 moles of hydrogen gas is needed if you want to make 3 moles of water. So the next question, here's our chemical equation, and it says here, what is the mole ratio needed to calculate the moles of KCl produced when 4.5 moles of O2 is formed? So you need a relationship between O2 and KCl. So O2 right here, okay, and KCl right here. So it's 2 moles KCl to 3 moles of O2. And you want to start with O2 here. So 4.5 moles of O2 needs to be converted to moles of KCl. And you know the relationship is 3 moles of O2 to 2 moles of KCl. I know I need to put the O2 on the bottom because the 4.5 to cancel off. I will need a 3 moles of oxygen on the bottom because it's 3 moles to 2 moles of KCl on the top. So my answer here will give me 3 moles of KCl. So when we usually have to solve problems with stoichiometry, what we want to do is number 1, make sure our equation is balanced. And they give you the amount of stuff in grams, you should convert them to moles because you can use the mole to mole ratio then to convert. So what you want to convert to, you make sure what you want to convert to is on the top. What you want to cancel off is going to be on the bottom. Once you get to the moles of the stuff that you want, after you do the mole to mole ratio, sometimes they ask you to get your answer in moles, then you're done. But if they ask you to get answer in grams, you just take the moles to convert to grams using the molar mass. Or sometimes they ask you for answers in atoms or molecules or ions, whatever. You will use Avogadro's number, which is 6.022 times 10 to the power 23 in 1 mole. So here's the flow chart. So if the question is given as grams of the first thing, you turn it to moles, and then you do the mole to mole ratio to what you want. Okay? If they give it to you in atoms or molecules, you can still turn it to moles and then do the moles to mole ratio to get what you want. And depending on what you get, sometimes if they ask you for answer in moles, you stop here. If they ask you for answer in grams, you use molar mass conversion. If they ask you for atoms and molecules, then you use Avogadro's number. So here's an example here. We have how many moles of CO2 will be produced by a reaction with 2 moles of glucose given the following balanced equation. So this equation here is balanced. Glucose is C6H12O6. And then we know that the relationship between glucose and CO2 is right here. 1 mole of glucose to 6 moles of CO2. And if you start with glucose, you put 2 moles of glucose and then you do the relationship between the mole to mole ratio of glucose and carbon dioxide, which would be carbon dioxide at 6, 1 mole of glucose. And you put glucose on the bottom because you want to cancel the glucose part off and you can get moles of carbon dioxide. So in this case, it will be 2 moles of glucose times 6 moles of carbon dioxide divided by 1 mole of glucose. So that part cancels off, and your answer is 12 moles of carbon dioxide. How many water molecules are produced when 0.010 moles of O2 react given the following balance equation? So 2H2 plus 1O2 gives you 2H2O. And they want you to find H2O as the desired unit, and you start with O2. So the relationship between O2 and water is 1 to 2. So that's our mole ratio right there. Okay, so then we're going to go ahead and do from the moles of O2 convert to moles of H2O. So when we have that, we have the moles right here. So O2 and O2 will cancel off. 2 moles of water is right here. But the question actually asks you for molecules. So then from the moles of water to convert to molecules of water, we know we use Avogadro's number. 1 mole of water on the bottom to cancel off is becoming 6.022 times 10 to the power 23 molecules of water. There you have the answer as 1.22 times 10 to the power 22 molecules. So here's the next question. How many moles of aluminum are produced when 0.5 moles of O2 react given the following balance equation? 4 of aluminum plus 3 of oxygen will give you 2 of aluminum oxide here, which is Al2O3. So our relationship here is going to be between oxygen and aluminum, where we know it's 3 moles of oxygen to 4 moles of aluminum, right there. Okay, and we're going to start with moles of oxygen on the top, so we want to keep the oxygen So 0.5 moles of oxygen, and then if you want to cancel off, the moles of oxygen should be on the bottom. So if we do that, this is what we look like. In this case, half a mole of oxygen is what you start with, and you know the ratio is 4 moles of aluminum to 3 moles of oxygen. Cancel the oxygen off, and then you do your math. 0.5 times 4 divided by 3 will give you 0.67 moles of aluminum as our answer that we need. What mass of H2 can be produced when 6 moles of aluminum reacts with HCl? So we want to look for the product H2, and you start off with 2 moles of aluminum. Our HCl here, we assume we have more than enough HCl, so aluminum is 2 moles, and hydrogen gas is 3 moles. So the relationship is 2 moles aluminum ratio to 3 moles of hydrogen gas. So if you start with 6 moles aluminum, you should put the ratio for aluminum on the bottom, 2 on the bottom, 2 moles of aluminum, and 3 moles of hydrogen on the top. We should be able to get our answer there. And that should only give us moles. Once we get moles, we will use molar mass, where one atom of hydrogen is 1.008, so 2 of the hydrogen is 2.016, and that should give us the grams of H2. So we start with 6 moles of aluminum. We cancel off aluminum on the bottom. We use the mole to mole ratio. Now we have moles of hydrogen gas. And then we use the molar mass to cancel off the moles of hydrogen gas. So 2.016 grams is to 1 mole. The 1 mole of hydrogen goes on the bottom, cancels off the moles, and you have 2.016 grams of H2 on the top to give your answer in grams of hydrogen. So to do your math, you do 6.0 times 3 divided by 2 times 2.016 divided by 1. And in this case here, this is an exact mole to mole ratio, and this is 4 sig fig, and this is exactly 1 mole, and this is 2 sig figs, so we keep our answers with 2 sig figs. How many moles of water are produced when 325 grams of octane CH18 are burned? So here's the balanced equation. 2 moles of octane plus 25 moles of oxygen gas will give you 16 moles of carbon dioxide and 18 moles of water. So you are really just looking for water in your answer, and they want you to get moles of water. So we have this mole to mole ratio of water and to octane here because we have the grams. So you have the mole ratio of water, 18 moles of water to 2 moles of octane. And then if we start from 325 grams of octane, we have to convert the grams to moles of octane, so we need the molar mass. So then you add up the values from the periodic table where carbon is 12.01, and then you have hydrogen is 1.008. You get your molar mass of 114.2 grams of C8H18 per every 1 mole. Okay, so we have the mole ratio from the balanced equation, and we can calculate the molar mass from the periodic table. So here's how we will calculate it. We'll start with 325 grams of octane. We convert it to moles first, so we cancel off the grams on the bottom. The moles of octane is on the top, and then we want to change the moles of octane to moles of water, so this goes on the bottom to cancel off. So when you do your calculation, it's 325 times 1 divided by 114.2, and then you will also change it to mole ratio, and you have 18 moles of water here to 2 moles of octane, and you get your answer is 25.6 moles of water. We keep 3 sig figs here because this mole ratio is unlimited sig fig, exact numbers. This is 4 sig figs, this is 3 sig figs, so our answer is 3 sig figs. So the reason why we stopped here is because they asked to answer in moles. If they were to ask the answer in atoms or grams, we'd have to take this and convert to whatever that is asked for. Here's another question. How many grams of AgNO3 silver nitrate are needed to produce 0.25 moles of Ag2S, which is silver sulfide? And here's our balance equation. 2AgNO3 plus H2S gives you Ag2S plus 2HNO3. So our mole ratio here that we're concerned of is going to be between Ag2S and AgNO3. Okay, so our goal is we need to make 0.25 moles of Ag2S. So we know the mole ratio of Ag2S, silver sulfide, and silver nitrate is 2 moles of silver nitrate to form 1 mole of silver sulfide. So we have the mole ratio there. And we need grams here. So if we start with 0.25 moles of silver sulfide, we use the mole ratio 1 mole of silver sulfide to 2 moles of silver nitrate. That should give us moles of silver nitrate. And then we have to use the molar mass of silver nitrate to convert to grams of silver nitrate. So we'll have to use the molar mass, which is 169.9 silver nitrate to 1 mole. You can calculate this from the periodic table by getting the number for silver, nitrogen, and 3 oxygens added up together. So when we want to calculate it, we start with the moles that's given in the question, 0.25 moles of silver sulfide, and we use the mole ratio where silver sulfide should go on the bottom, silver nitrate goes on the top, so we can cancel off the silver sulfide. The silver nitrate moles need to be converted to grams, so we put the moles on the bottom and the molar mass, the grams on the top here, and we get our answer in grams of silver nitrate. So you take 0.25 times 2 divided by 1 times 169.9 divided by 1, and you get 85.0 grams. And technically, if this was 0.25, this should just be 85 grams and 2 sig figs here. Here's the next question. How many grams of HNO3 are required? So this is nitric acid. How many grams of it are required to produce 8.75 grams of N2O? So here's our balanced reaction. We have 4 zinc plus 10 nitric acid will give you 4 zinc nitrate and N2O and 5 water. Okay, so this is dinitrogen oxide and this is just 5 water. This is just one of it. But we really need to be worried about the ratio between N2O and HNO3. So the ratio is 10 moles of HNO3 to 1 mole of N2O. If you start with grams of N2O, let's convert this grams of N2O using the molar mass to moles of N2O. And then we get the mole to mole ratio, which is 1 mole of N2O to 10 moles of HNO3. Then we have our answer in moles of nitric acid, HNO3. And then we got to use the molar mass of HNO3 to convert it back to grams of HNO3. So here are the values that we'll be needing. We have the mole to mole ratio. We have the molar mass of N2O and the molar mass of nitric acid. These can all be calculated from the periodic table. So we start with 8.75 grams of N2O, which is given in the question. We go ahead and convert to moles of N2O so we can start doing the mole to mole ratio. So the grams get canceled off on the bottom. Then you have our answer so far in moles, and then we want to do the mole to mole ratio N2O on the bottom so we can cross off with this. And then you get your answer in moles of nitric acid. And then we use the molar mass of nitric acid grams on the top, moles, 1 mole on the bottom to cancel off. So you get your answer as 125 grams of nitric acid. We keep 3 sig figs here because it's 3 sig figs, 4 sig figs, unlimited, and 4 sig figs. So this is also unlimited. So you take 8.75 divided by 44.02 times 10 times 63.02. That will give us our answer. So this is when dimensional analysis becomes really useful because you can do multiple steps all at once when you write out the formulas and convert from one unit to another unit, and then you get what you desire. Here's another question. How many grams of CrCl3 are required to produce 75 grams of AgCl? So this is silver chloride, and we need chromium chloride here, chromium 3 chloride to be specific, because this is 3 chlorine, so 3 negative, 3 Cl, each one is -1. This will be Cr3+. So chromium 3 chloride to silver chloride. So this is 1 mole chromium 3 chloride to 3 moles of silver chloride. Okay, and they start off with grams, so you'll need the molar mass of AgCl and molar mass of CrCl3. So you first take grams of AgCl, this one here, convert it to moles first. Then you take the mole ratio, 3 moles of AgCl to 1 mole of CrCl3. You get moles of CrCl3. And then you use the molar mass and convert this one to grams. So molar mass will be added from the periodic table. So these are the molar masses that we have here. And let's go ahead and put it in calculation. So we start with 75 grams, turn it to moles. So AgCl grams on the bottom cancel off. And then we do the mole to mole ratio. AgCl gets canceled off. Now we have moles of CrCl3. That's not enough because they asked for answer in grams, so we convert it to grams here by using the molar mass, and 1 mole CrCl3 goes on the bottom. That cancels off, and our unit is left in grams of CrCl3. So you keep 3 sig figs, 4 sig fig, unlimited sig fig, unlimited, 4 sig figs, and unlimited, so we end up keeping 3 sig figs in our answer. When you put it in your calculator, it's 75.0 divided by 143.3 divided by 3 times 158.4 will give you this answer right there, 27.6 grams. Now we want to talk a little bit about limiting reactants. So here's an analogy. If you want to make a bicycle, you need a lot of parts. We need to put parts together here. So we need some wheels. We have some frames. We have some pedals, okay? So if I have 8 wheels and each bike needs 2 wheels, I could potentially make 4 bikes, correct? And I have 4 frames, so then I could potentially make 4 bikes if I have enough pedals. And each bike needs 1 pedal. I only have 3 pedals, so that means I can only make 3 bikes. And then we have extra stuff. We have 2 extra wheels, 1 extra frame. We don't have enough pedal, so we couldn't make another bike. So what we end up making is just 3 bicycles. Okay, so this is where something we have limiting reactant and excess reactant. In this case, the thing that causes us to stop making our product, which in this case is bicycle, is our limiting reactant because we ran out of pedals. Pedals is a limiting reactant. And the other guys that we have extra of, like extra frame, extra wheels, those are excess reactants. Okay? And the 3 bicycles here that we make, this is the 3 possible, so it's a maximum possible amount of bicycles that you can make. This is actually also called the theoretical yield. Okay? And these are just the excess reactants that's left over. How much is left over? So here, that's a non-chemical analogy. Now we want to try to use the same analogy in chemistry. So here's a chemical example. If you have 5 molecules of H2 and 3 molecules of Cl2, how much HCl could you make? So we look at individual reactants and see how much they could potentially make, and then we end up being with a smaller amount. Remember, because like in the bike pedal situation, we ran out of bike pedals. Okay, so let's take a look. If I used all 5 molecules of my hydrogen gas, how many moles of molecules of HCl could I make? So if I do 5 molecules of H2, and I know that each one of them can give me the ratio of 1 molecule H2 can make 2 molecule HCl. Okay, so that would give me 10 molecules. And then let's take a look at for chlorine. So if I had chlorine, I have 3 molecules. If we started off with so 3 molecules of Cl2, and I know my ratio is 1 molecule of Cl2 to make 2 molecules of HCl. Okay, so in this case here, my answer would be 6 molecules of HCl that can be formed. So you can make 6 or you can make 10. But you know that once you make 6 molecules of HCl, you actually run out of Cl to keep going to make the rest of the HCl. So 6 is actually the maximum that we can make. Because after that we run out of chlorine and we don't have any more chlorine to react with the H2 to make more HCl. We're stuck. So we're stuck at 6 right here. Okay, so in this case, chlorine would be my limiting reactant. Hydrogen would be my excess reactant, and I know I'll actually have 2 molecules left over because I'll use 3 of them to make the 3 of them to react with 3 of the Cl here because I know the ratio is 1 to 1. So I know how much left over of my hydrogen too. So this is my theoretical yield, which is 6 molecules, my limiting reactant, chlorine, my excess reactant, hydrogen gas, and I'll have 2 left over of hydrogen gas. So a quick recap here. First thing you do is you always take how much product that you can make from each reactant. Just kind of see how much you can potentially make. Okay? And remember, we can only make as much as the smallest amount possible because we run out of stuff after that. So the reactant that gives the least amount of product is the limiting reactant, and the other reactants are going to be excess reactant. The amount of product that's determined that you can make over here will be based on the limiting reactant will be called the maximum amount possible or the theoretical yield. And then of course, if you want to find the excess reactant, you just find out how much of it was used up and then you subtract from the initial. So here's the question here that we can practice. It says how many moles of HCl can be produced from 4 moles of H2 and 3.5 moles of Cl2. So if I have 4 moles of H2, I could make 8 moles of HCl because I know it's 1 to 2. If I had 3.5 moles of Cl2, I could make 1 to 2 ratio. I could make 7 moles of HCl, right? So you see how this one can make 7, this one can make 8. Then obviously I will say Cl2 is my limiting reactant. H2 is my excess reactant. If I know that I can use up 3.5 moles of Cl2, I'll also use 3.5 moles of H2 because I know the 1-to-1 ratio here, and I know there'll be half a mole of H2 left over. So again, this is still simple. You can kind of see the math, but whenever it gets hard, we just use our dimensional analysis to show the calculations, and you can still get the same answers. So 8 moles of HCl there, okay, because we know the mole-to-mole ratio. And you take a look, this one here can make 7 moles. And that's how I say this was my maximum that I can make because after I make 7, I run out of Cl2 to keep going to make the last mole of product. So 7 is my max, my cap right here, okay? This is my theoretical yield. This is my limiting reactant. This is my excess reactant. And then if I want to find how much excess is left over, you just say, well, let's take a look at how much H2 was used up. Next question, how many moles of Fe3O4 can be produced from 16.8 grams of Fe and 10 grams of water? So you have grams of each one, so it's really going to be hard to tell just by looking. You'll have to convert grams of iron to moles of iron and then do the mole-to-mole ratio from Fe to Fe3O4. Then you can get an answer for the potential moles of Fe3O4 from this guy. And then you do the same with water based on 10 grams of water. Turn it to moles of water. 4 moles of water to 1 moles of Fe3O4. Get the moles right here. And then you can tell who's the limiting. The limiting is the one that makes the least amount of product. So the first option from Fe, you do the grams and then you turn it to moles using molar mass. And then you do the mole-to-mole ratio to get your product. You get 0.1001 moles here. So it's 0.100 here. Technically, we keep just 3 sig figs here. And then you have 10 grams here of water. You do the same thing with the molar mass, and you use the mole-to-mole ratio. You get 0.139. So you see here, this is smaller. So Fe is my limiting this water here will be my excess reactant. Next question. How many grams of AGBR can be produced from 50 grams of MgBr2 and 100 grams of AgNO3? So you need to take a look at our equation here. This is a balanced equation. So we have between how many grams of product can be formed here. So they're asking for the theoretical yield, which is how much of the AGBR can you actually make maximally. Okay, so you would have to take each reactant MgBr2 from grams, turn it to moles, and then do the mole to mole ratio of MgBr2 to AGBR to get how many moles of AGBR you can make. And then you can go one more step, just use the molar mass and turn this to grams as well. So you do magnesium bromide can make certain amount of grams of AGBR. You repeat the same process. 100 grams of silver nitrate here, you turn it to moles by using the molar mass, and then you do the mole ratio, 2 moles of silver nitrate to 2 moles of AGBR. And then once you get the moles of AGBR, convert it to grams here. So then you can find which one is the limiting and which one is going to give you the number of maximum AGBR that you can make. So the first option, from 50 grams of MgBr2, if you take a look, we use the molar mass of MgBr2, we cross off the grams, you get moles here, and then we take the mole to mole ratio, 1 MgBr is to 2 AGBR right here, and we convert to moles of AGBR. And then once you get to the moles of AGBR, we use the molar mass of AGBR here. We cross off the moles on the bottom. 1 mole of it weighs 187.4 grams of AGBR. You should get your answer in grams of AGBR that is potentially made. Okay, so if you use all 50 grams of MgBr2, you will make 102 grams of AGBR. Then we gotta take a look at the other one. 100 grams of silver nitrate, you turn it to moles using the molar mass. 1 mole AgNO3 is 169.9 grams of AgNO3. Cross that off. Get your answer in moles. Do the mole to mole ratio. This time is 2 moles to 2 moles right here. So we have now our answer in moles AGBR. And then you take that and convert to grams of AGBR right here. And you have 110.3 grams AGBR. Okay, so based on these two here, it is impossible for us to get 110.3 grams because once you make 102 grams, you actually run out of MgBr2 to keep going past 102 grams. So 102 grams AGBR is the maximum amount of AGBR that can be produced. This is called the theoretical yield, and this would answer that top part of the question. Now, the next thing we want to take a look at is we also have to determine how much excess reactant remains. So we clearly know that MgBr2 is our limiting reactant. We know AgNO3 is our excess. So from the previous question, we knew that MgBr2 was the limiting and silver nitrate is my excess. So you need to find out how much silver nitrate was used up. So all you do is you pair MgBr2 to AgNO3 to say if I use all my MgBr2, how much of the AgNO3 did I use up? Okay, so let's take a look. We have 50 grams of MgBr2, turn it to moles using the molar mass. And then we know the ratio is 2 silver nitrate to 1 MgBr2, so right here. And then you convert the moles of silver nitrate here to now use to grams of it, so using the molar mass. So that means in this case here, if you use 50 grams of MgBr2 here, you'll end up using 92.3 grams of AgNO3. So what did we start off with? Initially, we had 100 grams of AgNO3. If you use 92.3, that means we have 7.7 grams left over. So here's another question. How many grams of BaSO4 can be produced from 200 grams of BaNO3 and 100 grams of Na2SO4? So we have two reactants here, both have its own amounts. Based on this balanced equation here, you turn the 200 grams of barium nitrate to moles of barium nitrate, and then you find out how many grams of barium sulfate you can make. You use the multiple ratio, 1 mole of barium nitrate to 1 mole of barium sulfate, and then you get your moles of barium sulfate here. You can use the molar mass to turn it to grams of barium sulfate. So that's just for one reactant here. You repeat the same thing with 100 grams of Na2SO4, turn it to moles of Na2SO4 using the molar mass, and then you know the ratio is 1 to 1 again. Find out how many moles of BaSO4 is made, convert it to grams of BaSO4 potentially made using the molar mass. Let's compare those two. So the first one with 200 grams of barium nitrate, if you follow through the steps here that we just described, first convert it to moles, and then mole-to-mole ratio 1 to 1, and then convert it to grams of barium sulfate, you get potentially 178.6 grams of barium sulfate being made. If you use the second reactant, 100 grams of sodium sulfate, you convert it to moles, and then you do the mole-to-mole ratio, which is 1 to 1, and then convert it to grams of barium sulfate using its molar mass, you get 164.4 grams of barium sulfate. So in this case, your 164.4 grams barium sulfate is the max you can make, because once you make 164.4 grams, you run out of sodium sulfate. You can't keep going to make more than 164.4. This is my maximum amount of barium sulfate that can be made and called the theoretical yield. So that means I know I have excess of barium nitrate. So how much barium nitrate is left over, we can easily calculate that if needed. But I don't think they asked for you for that question here, how many grams can be produced. So really our answer just ends here. So we had a different question that they asked further how much leftover of this guy was. You would do the same thing that we did in the previous question, where you find out if I use all 100 grams of sodium sulfate, pair it with barium nitrate, find out how much barium nitrate will be used, and then you just take what was used away, subtract it from 200 grams of what you had initially, you will find it left over there. So, but again, all you have to do in this question is find out the theoretical yield. In this case, is 164.4 because sodium sulfate is my limiting reactant and barium nitrate is my excess reactant. So here's another question. The question says, calculate the number of moles of excess reactant that will be left over when 50 grams of Ki react with 50 grams of Br2. And here's our equation. 2Ki plus Br2 goes to 2Kbr plus I2. Here's all the molar masses are provided. So so what we traditionally have been doing is, first of all, find out who's the limiting reactant, right? You can pick either product, one of them, and see who can make the smaller amount of product, and that's the limiting. And then you find out from the limiting how much of the excess was used up. Okay, so that way works. It's just the same way like we did a couple slides back. You can try that. I want to show you an alternative way to do this because now they are not asking you for the theoretical yield of any of the products. So we technically could skip that step. What I would do is now, let's imagine if I use all of my Ki here, all 50 grams, how much of the Br2 will I need? And then I calculate the same thing. If I use all 50 grams of Br2, how much Ki would I need? And then we'll see which one was short. And that's how you can also tell who's the limiting without having to go to the products. So if they don't ask you about the products, you can technically skip this step. But if you're not too sure about this way, you can always stick to the step. Pick one product. I would say either I2 or KBR, whichever one you prefer, and decide how many moles of it that you can make. And the smaller one will basically, the smaller amount of product comes from the limiting reactant. Okay, and then you can find out who's the excess and how much the excess was used. Do the same thing. So what I'm going to show you is an alternative way to calculate this. So what I want to do is, the first thing I want to do is I'm going to go ahead and calculate if I used 50 grams of Ki, how many grams of Br2 will I need? Okay, so if I start with 50 grams of Ki, I need to turn it to moles first. So 1 mole of Ki is 166.00 grams of Ki. And then the mole-to-mole ratio is, in this case, 2 moles of Ki to 1 mole of Br2. Okay, let's turn this to grams. Also, I'm running out of space, so I'm going to write a little smaller. 1 mole of Br2 is going to weigh 159.81 grams. This is Br2. Okay, now let's go ahead and put this in the calculator. I would do, because you see how I'm crossing out the grams here, and then I cross off the moles, and then I cross off the moles of Br2. I get my answer in grams of Br2. So if I used all 50 grams of Ki, how many grams of Br2 would you need? You would put in your calculator 50 grams divided by 166 divided by 2 times 159.81. Okay, so in your calculations, this should give you 24.1 grams of Br2 needed. Okay, so is this possible? If I use all 50 grams of Ki, I will end up using 24.1 grams of Br2. That's possible. That makes sense. Okay, so that means if I do the other one, it's going to be like an impossible option because 24.1 grams of Br2 will be paired with 50 grams of Ki. So if you use 50 grams of Br2, you're going to need a lot more of Ki, more than 50 grams. So if you did this and you see that this is logical, the other way is not logical, you can skip that step. But I'm going to show you anyway. Okay, so let's do the other one. The other step is going to be if we use all 50 grams of Br2. Let's go ahead and turn it to moles. 1 mole of Br2 is 159.81 grams. And then our mole-to-mole ratio is 1 Br2 to 2 moles of Ki. And then we turn it to grams of Ki. 1 mole of Ki from the molar mass weighs 166.00 grams Ki. So this will give me an answer of 103.87 grams Ki needed. You see how this is impossible? So this one here is impossible, since we only have 50 grams of Ki. Okay, so that tells me Br2 is excess, Ki is my limiting. Okay, so Ki is limiting. Let's write it down. So this one is my limiting, and then Br2 is my excess. In fact, we already know how much Br2 is used up. Okay, so let's write that down. So if you know Ki is limiting, Br2 is excess, and we started off with 50 grams of Br2, okay, we use 24.1 grams of Br2. And then that will give us the leftover if you took the difference there. So you get 25.9 grams, 25.9 grams of Br2. Okay, so this one is leftover. So the answer actually wanted you to find it in moles of Br2. So let's go ahead and convert 25.9 grams to moles, okay? So 25.9 grams of Br2, 1 mole of Br2 is going to weigh 159.81 grams. So in this case, you get 0.162 moles Br2 left over. So our answer would be D, right there. Alright, so let's talk about reaction yield. So far when we calculate them, we've always said this is a theoretical yield, which is the maximum yield possible. Okay, so that's always 100%. A lot of times when you do experiments, our yields are usually lower than 100% because we have side reactions. Sometimes we lose product while transferring material or maybe purifying it. So it's always going to usually be less than 100. Okay, but theoretical yield means 100% is the maximum possible yield that you can make. Actual yield is what you actually do, what you actually get from after the experiment. So theoretical yield is what you calculate to be 100% possible, and then sometimes you don't get 100% of what you want. You lose some to transfer or purification, so you get less than 100%, and that would give you your actual yield. So if you take the ratio, you take actual yield divided by the theoretical yield times 100, you get the percent yield right there. So remember, actual yield is what you get in the experiment. Theoretical yield is what you calculate from the reaction. And you take actual divided by theoretical, you get percent yield right there. So let's go ahead and have a question where we can calculate percent yield. In this case here, AGBR, calculate the percent yield of AGBR. Okay, you start with 375 grams of the compound. So 375 grams of the compound, they are prepared from 200 grams of MgBr2. So you have to think, if I use all 200 grams of MgBr2, how many grams of AGBr can I make? And then once you do that, you get that, they're assuming you have excess of silver nitrate here. Okay, so let's find out what the theoretical yield of AGBr here based on 200 grams of MgBr2. So if you want to do that, you do the theoretical yield. You take grams of MgBr2, you turn it to moles of MgBr2. We do the mole to mole ratio. 2 AGBr, 2 moles of it is made from 1 mole of MgBr2. So you see here 2 moles of AGBr on the top, 1 mole of MgBr2 on the bottom. And then once we get AGBr, we convert it to grams of AGBr. So potentially you can make 408.0 grams of AGBr. That's my 100% theoretical yield. And they say they only made 375 grams when they did the experiment. So to get the percent yield, you take the 375 grams, the actual yield divided by the theoretical yield you calculated times 100, that's 91.91% right there. So here's another practice question for percent yield. It says calculate the percent yield of Al2O3 if 125 grams of Al gives 100 grams of Al2O3. So let's find out how many grams of Al2O3 can be made from this reactant here. We are assuming this guy is excess. Okay, if they don't mention it, it was the excess. If they want you to figure out who's the limiting, they have to give you both amounts here. So let's go ahead and do, first thing you do is you take grams of aluminum, turn it to moles of aluminum, and then you do the mole to mole ratio. 2 Al is to 1 Al2O3, and then you can get the grams of Al2O3 by using molar mass. So that would give us the theoretical yield. So 125 grams of aluminum, turn it to moles, mole to mole ratio, and then turn it back to grams of Al2O3. Our theoretical yield in this case is 236.3 grams of Al2O3. So they say they made 100 grams. Okay, so to get the percent yield, you take the 100 grams divided by 236.3 grams times 100, which gives you a percent yield of 42.32%. So here's another question where we have to do a calculation where they have a following reaction: PCl3 plus Cl2 goes to PCl5. If the percent yield is 66.3%, what mass of PCl5 is actually formed when 61.3 grams of Cl2 reacts with excess PCl3? So remember, they're assuming this one you have more than enough of, and you react all of 61.3 grams of Cl2. So first of all, you probably want to find out if it was 100%, what it would be, because you can calculate that from the reaction. So you want to find out if I use all 61.3 grams of Cl2, okay? How many grams of PCl5 can you make? That would be the theoretical yield 100% right there. So once you get the 100% number, you say, well, it says the percent yield is 66.3, so that means it's just 66.3 of my theoretical yield. Okay, so we'll get there. So let's turn it to moles of Cl2 first. So 1 mole of Cl2 is going to weigh 70.91 grams of Cl2. Okay, and then let's do, once we have moles here, let's do the mole to mole ratio. 1 mole of Cl2 is to 1 mole of PCl5. Okay, so we get 1 mole of PCl5 here. Now we want to turn this into grams of PCl5. So 1 mole of PCl5 is going to weigh 208.24 grams of PCl5. So you see, when we did the math, we couldn't cross off the grams. We have our moles of chlorine, cross that off. We use the mole to mole ratio to get moles of PCl5. Now my answer is going to be in grams of PCl5. This here, it says, if I use all 61.3 grams of Cl2, I can make a certain amount of PCl5 in grams. Okay, and if you put this in your calculator, 61.3 divided by 70.91 times 208.24. I just ignored it once. You can do is, times 1 divided by 1 and divided by 1 is the 1. So you put that in your calculator, you should get an answer of 180 grams of PCl5. Okay, so let's go ahead and put that down. 180 grams of PCl5. So this here is my theoretical yield, because we're saying this is straight up from calculation. This is my 100%. Okay, so you know that 100% is going to be 180 grams. So if you need 66.3%, that's my percent yield, right? 66.3%, and you know 100%. You see how I'm crossing off the percent here? Is 180 grams of PCl5 right there. Okay, 180 grams PCl5, 66.3% of that is going to be 119 grams of PCl5. Okay, so that should give us our answer. Our answer in this case is going to be C right there.